All right, chapter 9. So, chapter 9 in the old book was split up into two different chapters, actually. The first chapter was Center of Mass and Conservation of Momentum, and then that was chapter 9, and then chapter 10 was Collisions. And so, this book, your new book, decided to put them all into one chapter. So, I'm going to keep them sort of split up and do 9A and 9B. 9A, again, talks about center of mass, which is really the first main concept, and conservation of momentum, which is the second and the third concepts. And there's also a couple problems that you'll do from WebAssign dealing with rockets, basically variable mass problems, and because we're assuming that the mass is constant in these problems, although in some problems the masses will split up, like you might have an explosion, things break apart into multiple pieces. But in rocket equations, rocket type problems, the mass is continually decreasing as the fuel burns out. And so we'll do a couple questions on that as well. Almost seems like an aside, but it is related to these. So the first main concept is the center of mass. Every object has a center of mass, and one way of intuitively seeing that without calculating is to try to balance an object. Say on your finger, if you take, maybe if you're holding onto a pencil right now, take your pencil and try to balance it on your finger so it doesn't tip to one side or the other. Then you know your finger, if it is balanced, your finger is right below the center of mass. You also have to realize that the center of mass is not necessarily halfway up the pencil from where your finger is, but at least you know that your finger is below the center of mass. But there is a way to calculate an object's center of mass, and here's an equation using point-like objects as the center as the masses. And you'll also notice that you can replace position with velocity, and yet again you could also do that with acceleration to get the velocity of the center of mass of an object. Basically the same question, same equation. You might also notice, although it's not really super important, but the equation for momentum is mass times velocity, and so you could probably replace these with momentums, momentum of object 1, momentum of object 2, and that is essentially sort of hidden in the velocity center of mass equation. Other things to think about for the center of mass: the center of mass is halfway between two objects of equal mass, and you could probably realize this intuitively, but if you want to test it out, take a meter stick, and your finger should be able to balance the meter stick when you place your finger at 50 centimeters. Because if they made the meter stick appropriately, then it'll have the same amount of mass on either side of the 50 centimeter mark. If it doesn't balance, then maybe there's a knot in the stick, in the wood of the stick at one end or something that might make one end a little heavier. But ideally, if they made the meter stick perfectly, then your finger should be able to balance at 50 centimeters. But the center mass is closer to the more massive of the two objects. So take something like your calculator or an eraser and put it on one end of the ruler. You'll notice your finger has to move much closer to the calculator in order to now balance the meter stick. The center of mass of a uniform object is at its geometric center, and I'll go into more detail about that with a picture. But this equation, we're assuming that we're dealing with point-like objects. But in real life, there's really no such thing as point-like objects. All objects take up a certain amount of space, or even volume, I should say. So the center of mass of these non-point-like objects is at the geometric center of an object. Not all objects are very easy to find the geometric center of, but some are much easier than others. And when dealing with uniform objects, instead of you may not know its mass, but if it's uniform, that means it's the same density all throughout. Then the area of the object is proportional to its mass. So if you have, well, no, I'll go into more detail on that later. I just want to give you an overview of the main concepts. So then the second main concept is momentum. Momentum, with lowercase p, is mass times velocity. There is no special unit for momentum. Like force, it's a Newton, which is a kilogram meter per second squared, mass times acceleration. But for momentum, there's no special momentum unit. It's just kilogram times meter per second. Kilogram for mass, meter per second for velocity. Momentum is a vector because velocity is a vector. So when you add momentums up, you have to keep them in component form. And also for conservation momentum, these equations only hold true in one direction. So if you have momentums at strange angles, then you'd have to do momentum x equals momentum x, momentum y equals momentum y. Speaking of which, the third main concept is conservation of momentum, and that says that any momentum in a system is conserved. It just changes from one object to another. It never disappears or magically appears. So the initial momentum in a system equals the final momentum in a system. But if you've ever played billiards or pool, then you know that the velocity of the pool balls aren't always the same. Like when you shoot one ball, like this may be the 8-ball at rest, so it has no momentum initially. Then you shoot the cue ball at it. The cue ball has a high velocity, but then afterwards, when they hit, suddenly the 8-ball has some velocity now. But that doesn't mean that new momentum was created for the 8-ball. It just means that momentum from the cue ball was transferred. So anyway, yeah, so that's conservation of momentum. And then rocket equations. The problems in your textbook are very relatively simple problems. And basically, this is the rate at which fuel is being consumed, R. This is the relative velocity of the fuel coming out of the rocket relative to the actual rocket. And this is the force of the thrust of the fuel coming out of the rocket. And you can also relate the relative speed to the change in speed of a rocket. So you'll know that as a rocket burns fuel, the mass of the rocket gets lower because the mass of the fuel is being ejected out the back. So the final mass is going to be lower than the initial mass. And so any thrust acting on lower and lower mass will give you higher and higher acceleration. So you can calculate your change in velocity based on how much mass is being lost. Yeah, so let's start talking about the first main concept, center of mass. I have a few different things to show you here, so I think in this first video I might only get through this one and maybe this one here, and I'll talk about uniform objects, these two are here for these pictures, maybe in the next video. So let's start with this one. We have two point-like objects, M1 and M2. And when I say point-like, I mean they take up basically no space. They drew them bigger here just to emphasize that M2 is more massive, but being point-like objects, they take up no volume, no space. So essentially where they're located is their position in this equation. So if you wanted to figure out this x-com here, so here's the xy axis. M1 is at 0, 0. M2 is at d0. Right? So the center mass is at what position? So we'll use this equation here. X center mass equals M1, so however massive M1 is goes there. X1, which would be 0, so this term would actually disappear, plus M2, which is bigger than M1, times X2, which on this diagram is D. Then you divide that by the sum of the masses, so M1 plus M2. So even though M1 has a position of 0, its mass still plays a role in the center of mass location. And these dot dot dots just mean that if there's more objects, you just keep doing like M3 plus X3, or M3 times X3 divided by M3 here. But in this picture, there's only 2 objects. What else do I want to say? Oh, so notice this first one here. The center of mass is halfway between 2 objects of equal mass. So if M1 and M2 were equal, then the center mass would probably be right about there, about halfway. It would be at halfway, but that's the best I can draw it. But it's closer to the more massive of 2 objects. M2 is more massive, and so you can see that the center mass is closer to M2 than it is to M1. if you suddenly, if you shift, so nothing really has changed about, say, the distance between M1 and M2 over here. The only thing that's changed is the location of the origin. It's shifted to the left. And so all that does is it makes this term right here non-zero because M1 is no longer at the origin. It's at x1. So you still have M1. Now x1 is a value, some value here, which you stick in there. M2 now is at x2, which is d plus x1. You can see here x2 is this whole length, which is d plus x1. And now xcom, excuse me, xcom, the x center of mass, is still going to be what it originally was over here, this length from M1 to the pink dot, plus x1 now. So anyway, this is basically showing you that this equation is valid for any system, whether you set one of the masses up at the origin or you set the origin off somewhere to the side here. And if these objects were moving, which you could use kinematics, right, to figure out, say, speeds and whatnot. Oh, there should be a 1 here. Whoops, typo. If these objects are moving, then you could simply use this equation, just like you used the x equation, to figure out the velocity of the center of mass. Usually you would do it at a certain time. Some of these objects might even be accelerating, and so they won't have the same velocities always. So at that point you would have to do it at a certain time. And yeah, I got some time, so let's talk about this one down here. So sometimes the objects aren't all in a straight line like these are. So you have M1 here at the origin, M2 is on the x-axis over here, so these two are kind of like the first situation I was talking about up here. But now we have M3 up on the y-axis, and so the center of mass is now shifted up the y-axis a little bit. So because momentum is a vector and displacements, position is a vector, and velocity is a vector, then you need to treat these like components. So what you do is use the same equation, but then you would go like x com in the x direction equals m1 x1 plus m2 x2 plus m3 x3, and then you have y com in the y direction. Well, we don't need these actually now that we've called it x and y, whatever. And that would equal m1 y1 plus m2 y2 plus m3 y3. And we shouldn't forget over the total mass. I did big M, but big M means m1 plus m2 plus m3. Right? So what are these values? x1 is 0, so that just becomes 0. m2 is at, what's this, 50, 100, 110, 120, maybe 140. So plus m2 times 140, and m3 plus m3 times, looks like it's at 50, 60, 70. So just the x value for that, of course, divided by all the m's. Whereas over here for y, you do m1 times 0, still at 0y, plus m2. m2 is also at 0 because it's only on the x-axis, plus m3, and m3 is up 100, 110, 120. And then you divide that by the total mass. So that gives you the x and y components of the center of mass, which if you look over here, the x component is 50, 60, 70, 82-ish, and the y component is 58-ish maybe. And then you could do Pythagorean theorem to get RCOM, the actual one right here. So yeah, so in the next video we'll talk about uniform objects, non-point-like objects like these disks here, and go from there. All right, later.